Hello there, my name is Charles Swasfan Msipa. Welcome to another presentation of our e-tutorial series. In this case here, I would like to engage the concept of differentiation versus that of integration and explore and understand what is their relationship. Right, let's start this way. Let's say we've got this kind of diagram here. On the left here, we've got functions like x squared, 2x and c, which is a constant function, and sine x. And moving in this direction, we get to another set of functions where we've got cosine, 0, 2x, and 2. So here we know that this is the notation for differentiation. Now as when we write this here, we know that the operation we're going to do is differentiation. So what we can do, we can actually try to see if we part from x squared by differentiation, which function will end it here. I think it's clear to all of us by now that 2x squared will lend us at 2x, and similarly a constant function will lend us at 0. So in this case, we're talking about the differentiation. So this schema is we're having this schema to illustrate that the fact that differentiation is actually the opposite process of what we're going to learn, which is called integration, and symbolized by this sign, which we call the integration sign. The integration sign is a mathematical sign operation, like we've got a plus sign, minus sign. So now, if we were to part from this side, it is clear to us that if we have 2 as a derivative, we know that this 2 as a derivative came from 2x. So in other words, following this rule, these 2 will be taken to 2x, and similarly our cosine will be taken to that. So like illustrated in this diagram here, integration and differentiation are opposite processes, or what you can call inverse processes. In other words, inverse in what maybe we can parallel to opposites in our everyday language. So these are kind of opposite processes. I will emphasize that word they're opposite, because I want to start from the very, very concrete and understand it as an opposite operation. Now let's turn to this kind of schema. We know that here we've got a function, and these functions here we've denoted them by capital letters on purpose. Like here we call this function capital letter f of x, and here capital letter y, which is given by that. And what I would like you to notice that, or what I want to invite you to do, compute the derivatives of these functions. Let's start, for example, by the first one here, which is x to the power n plus 0, or which you can just simply write as x to the power n. Differentiating this, we know that we normally do our power rule as follows: we put down x, we multiply by x to the power n minus 1. Now if we check all these functions, they will differentiate to that same expression. Now as if you were to complete this, we would write here that the derivative of all these functions is nx to the power n minus 1. You can check that. So in other words, when we are differentiating and we've got an expression of a derivative here, we can see from what we were experiencing here that this expression won't be from a single function, but from a family of functions. Like we have here x squared, x to the power n. Note that if we've got a function like this as a derivative, we must understand that it's not a result of differentiating a single fraction, but it's differentiating a family of functions like we've got here: x to the power n plus 0, x to the power n plus 5, x to the power n plus pi, or any other constant which we can generally represent it this way. So now the process of differentiation going in this direction is the opposite of integration, which is going to go in that direction. So now if we were to say this is a derivative and we want to find out of which function it is, any of these functions is a candidate for that as an answer to that question. But in this case, we must choose the best candidate, which is going to represent all these functions. And I think if you check properly, that candidate will be this one, because C covers all these constants we have here. So to do that, we use the integral sign, which at the moment we can take it as an equivalent of a question mark. What's this question mark? What's this question asking? Is asking, here is a derivative for which function it is. So when I write here now, I write here is a derivative n x to the power n minus 1, a derivative with respect to x, write that dx for which function it is. So any of these functions are candidates to answering this question. But like I've said, we'll choose the best candidate in this case, which is this one. So we would write that as xn plus c. So what we are saying here, we're saying that the function under the integral sign is a derivative. We write it for process of differentiation. And now when we put the integral sign, we are like asking the question, whose derivative or for which function is this one a derivative? Then like we're seeing here, we would like answer this question this way. So maybe summarizing, we would have something like this, whereby we've got that general power rule derivative, and when we ask the question for which function is this derivative of, we can answer x to the power n plus c. Usually things are not so simple. It's because I'm trying to make you understand how differentiation relates to integration, and the c here covers all the possible constants which can be added to this power function. Then next, let's look at this case. If we differentiate again here, I hope you can see that here we need to apply the chain rule for all these functions. Sorry, here is supposed to be n, not 3 to the power n. So if you differentiate each one of these, this one is plus 0, this one x squared plus x to the power n plus 63, x squared plus x to the power n minus 80, and another constant here until we get to this most general expression. We'll say the derivative of all this family of functions is n in brackets x squared plus x to the power n minus 1 multiplied by derivative argument in this case, which is going to be equals to 2x plus 1. Okay, so we see that so the common derivative for all these functions here, or for this family of functions, will be n in brackets x to the power 2 plus x plus 1 as the argument of the power function here, power n, multiplied by the derivative of the argument. So this is the usual way we differentiate a function. So now during the reverse process, which is differentiation, we'll be taking this derivative, like we've said before, under the integral sign. In that case, the integral sign is asking us that here is a derivative where for which function is it. In other words, we can now directly say that it's for this function, or we can say that function or that. But to choose a best answer for that, we choose the most suitable candidate here, which is this one. So I hope this makes you understand that when you are differentiating, you arrive at a derivative, but now when you are reversing the process, you cannot necessarily pick this because this one missed out and this one be left out, and any other function, similar function with added constant will be left out. So in order to cover everything, we choose this one. Hence, in that summarizing, we would have this like this. You see that this is the derivative of the argument. So in general, what we have here is we have something which you can say there. We've got our function which we started with there, which we can write as f of x to the power n. So this is power n minus 1 multiplied by this, which is f of x prime integrated with respect to x. This is what we have in generally as a integral of involving power functions. Then we're going to later develop an analytical approach of how we can compute the integral. And another word used for this, we would call this function a derivative, and this function will be the antiderivative of that, or the integral of that function. Now proceeding, let's look at this. So now what we have now, if we've got a function like this, it will differentiate to that, and if we've got a function like that, it will always differentiate to that. Now we want to proceed to a situation where how do we compute the function which was, how to compute and arrive at the function which was differentiated if we've got this or that. Maybe let's start simple. Let's start with this one. Let's say we wanted to reverse this process and get emphasizing on the fact that these are opposite processes. I think to get to see what we were supposed to do, we must notice that the power which was given here is power n. To arrive to this power here, we arrive by subtracting 1. So in this going in this direction, I think we can retain this n and write that x and say x minus 1. And now if we do the opposite of what was done here, we would add 1. Now this power which we have here will result in x to the power n. Then our problem now will remain being this n which we don't have there. But we see that if we carry out this operation, we're going to get this equals to n. Now our problem with this n, which is multiplying. Now if we emphasize again on the issue of these operations being opposite, so do what you can consider to be the inverse or a kind of an opposite to multiplication, which means now we would divide by n. But how could you arrive at that n? We could arrive at that n by taking the same n minus 1, writing n minus 1, doing exactly what we did there, and adding a 1. Then what is left here, this will take us to n, x to the power n, resulting from here, divided by n, and then this simplifies to x to the power n, which is exactly what we've got there. Now, if we analyze this properly, what has actually happened is that we took the power which was given here as the power for the function which we're integrating, we increased by 1 as opposed to decreasing by 1 when we went thus. And we also divided by this same power head here, which is now going to be, which is also going to be n minus 1 plus 1, and you get that arrived there. Then here is going to work exactly the similar way, but I think it's more complicated to analyze this way. Because of this, we'll check that, we'll look at that later and try to understand it. Now let's see what to generalize this one. Let's suppose we're given a function x to the power k dx. So doing what we did here, we'll take this power which is given, increase by 1, which means we're going to get x to the power k plus 1. We're increasing as opposed to decreasing when we're going that side. Then when we went that side, we actually multiplied by the power which we're given. So now we're going to divide this by the power which we've just obtained by 18, right? And then because of what we said before, that the most appropriate candidate for being an integral of this type of function will be the case when we've added a c. So we write here and say c to cover all the possible constants which would be added to the function. Then we can write here that c would be a real number. And again, we need to be careful here that when we've got this kind of division, we are not allowed to divide by 0. So we should emphasize that k must be different from minus 1. Otherwise, we're going to get this expression undefined. Now, unpacking this further, notice that if we've got y to the power, y is equal to x to the power n, and differentiating, applying the chain rule in its general form, we'll say y prime is equals to nx to the power n minus 1 multiplied by the derivative of the argument of the power function. In this case, the derivative of the argument of the power function here is the argument of the power function here is x. So if we apply the chain rule and say multiplied by the derivative of the argument, we would say multiplied by the derivative of x with respect to x, which is equals to 1 dx, which is equals to 1. So now that says to us what we have here actually is the derivative. Here we've got x to the power n to the power k multiplied by 1 sitting here as a derivative of the argument of this function, multiplied by dx, and we get this integrating as x to the power k plus 1 over k plus 1 plus c with the same condition for k. Now, if we now consider this type of function, we can actually interpret it exactly the same way like this. Let's see how we do that. We take x integral of f of x to the power k multiplied by f of x prime multiplied by dx. Now here, what we're trying to do is we're trying to exploit this structure here and take it to this kind of. Now, let's see this. If we try to strike some parallelism here, we'll say this one here as a derivative argument is parallel to f prime, and this x is parallel to our base here, which is f of x, and the power to the power, and dx is parallel to. Now, if we read properly what is being said here, if we've got this kind of derivative, it is a power function multiplied by the derivative argument, in this case which is 1, and in general here just f prime. What we do is we would retain the argument of this power, but increase the power by 1, and then divide by the new power, which is k plus 1, and then add c. Now, mimicking that would do exactly the same. Now, mimicking this would have this equals to f of x, like I retained the x here there, I'm retaining my base there, which is f of x. Then I increase this power by 1, and likewise divide that by 1, divided by k plus 1, okay, divided by k plus 1, and then like choosing the most general situation for this derivative, we'll get that plus c, and emphasize again that k is different from 1. So now, what we've taken advantage of here is the how the chain rule works for the power function, and they try to strike some similarity with that. Here again, you can apply chain rule and they strike this kind of similarity, and they do exactly the same kind of operation we did here with a function f of x, which can be any function, can be trigonometric function or a polynomial function elevated to a power. Will do exactly this way, as long as the structure we have here is a structure of a derivative of a power function, which will always function elevated to power multiplied by the derivative of the base here. Okay, summarizing our discussion above, we get to what we call power rule for integration. In this case, what we have here, looking at this as a power of x, a simple power, a simple argument x, and we can consider it having exactly the same structure like this, and like we showed above. So this will be integrated this way as long as n is different from 0. And in general, if the base of the power here is any function f of x multiplied by the derivative of this argument, then that will be integrated as f of x to the power n plus 1 divided by n plus 1 plus c, and again the condition that n is different from 0 must be satisfied. So in this case here we've got the form of a general antiderivative of this kind of a power function derivative. So now what we can do now, we can proceed and look at the examples. Here we got an example. What we're integrating here, we're integrating integral of x squared plus 2x to the power 3 and multiplied by 2x plus 2 dx. If we look at this, we can sort of try to strike some parallel with the general form which we looked at before, which is integral of f of x to the power n multiplied by f of x prime, the derivative, the argument here, multiplied by dx. So what we've just seen above is that this will integrate to be f of x to the power n plus 1 divided by n plus 1 plus c. So whenever we get such a kind of a function and integral, we should try to analyze and see if what we've got here has this part as its derivative, or a partial derivative which you can somehow compensate by multiplying or dividing to get the derivative by a constant. So now what we have here, we have exactly this situation. So following this formula or mimicking this formula, we would say this is equals to x squared plus 2x to the power 3 plus 1 over 3 plus 1 plus a constant c, and this will give us x squared plus 2x all to the power 4 divided by 4 plus c. So now when you get here, what we'll be saying is that this function is the function which, when we differentiate with respect to x, it gives us this function under the integral here, which we can check by using our knowledge of differentiation. Let's differentiate this function and see whether we get that. So let's say we denote that function, this function by y is equals to x squared plus 2x in brackets to the power of 4 divided by 4 plus c. Now to get this derivative, let's denote it by little y and differentiate that. So our derivative here, using the power rule, we'll take 4 down and say 4 brackets x squared plus 2x bracket to power 4 minus 1 multiplied by the derivative of the argument of the power function there, which is 4. The derivative argument will be the derivative of this function, which will be 2x plus 2 divided by this 4 plus a constant c. So simplifying here, we can see that this 4 and this one, they give us a 1. Then we have got this as x squared plus 2x to the power 3 multiplied by 2x plus, sorry, here we're supposed to write derivative of the constant function with respect to x, not only c. Then this will be plus 2, and the derivative of the constant function, remember we're differentiating this function to check if it gives us the integrand there, the function under the integral sign. So the derivative constant here will be 0, so that will be plus 0. Now if we check that, this simplifies exactly to what we've got under integral sign, which is x squared plus 2x plus 3 multiplied by 2x plus 2. So this again confirms to you that the process of differentiation and integration are opposite, or say inverse processes. So this means that whenever we're given an integral sign, we must see what is under integral sign as a derivative or something, some function which is transformable to a derivative which we know, and then answer the question that this is a derivative of a function which looks like this. And if ever we suspect that maybe we've done some kind of miscalculation or some slip of a pen and written something wrongly, we can do the checking by differentiation and see that what we get after doing our differentiation correctly is exactly what is the under the integral sign. Now our next example is as follows. Let's say we've got here integral of sine to the power 3 multiplied by cos. Most important, when you see a power, we must reflect and ask ourselves, is it this form of an integral? Now it's in form of a power rule integral, which is given by f of x to a power multiplied by the derivative of the argument of the power function with respect to the independent variable, in this case, which is x, and which by now we should be knowing that this will take us to f of x to the power n plus 1 over n plus 1 plus c. So what we have here, we can see that our f of x is sine. So now we need to check whether what we have here is the derivative of our f of x. Now, how do we check that? We could just check that by taking derivative of with respect to x of sine x, and by now we should be knowing that this derivative is cosine x. So this situation is satisfied here. So we can now say the integral here is sine. You see, as you can see here, we retain the argument of the power which we've got there. There it is, f of x. What we do is we increase the power 3 plus 1, divide by 3 plus 1, and add constant c. So now we can say now this function you can call here y of x is equals to sine, which you can write also as sine power 4 this way without using the brackets, x over 4 plus c. So now we can now check that when we move in the direction of differentiation, what we do is we take derivative of y with respect to x using the power function, the power rule again. We'll say 4 sine to the power 3 is 4 minus 1 over 4 multiplied by the derivative argument of the power function. In this case, the power function is f of x equals to the power 4. So it's a 4 power function whose argument here is sine. So then you multiply this by the derivative argument, which is called sine x, plus the derivative of this constant, which is 0. And you can see that this simplifies to what we have under integral sign, which is sine to the power 3 x cosine x. So I hope up to this stage it is clear how differentiation and integration relate. So the most important thing is that you have to be very thorough with your differentiation in order to be able to integrate. Maybe just to give you a feel of, because what we have here is like given like manna from heaven. We just play around with the same thing and get the answer. Let's see how we could get a more challenging exercise, which would need also our analytic skills. Let's say with something like this, we got x, we saw the integral of x to the power 3 plus 3x, all this to the power 2 multiplied by x squared plus 1 dx. This one, if we try to check what we have there, we will see that we don't immediately get it the way. Now, if we try to check what we have here, we will see that we don't immediately get what a simple case which we have there. Because if we check if this is just a power function which has got this similar structure but a different function, a polynomial here, there it has a trigonometry. But when we check whether this is the derivative of that, we see that not really, but partly yes. Then we can now analyze this thing, that what are we short of here in order to have a derivative of that. We can see that when we differentiate this with respect to x, we get 3x squared, and we've got x squared here. And when we differentiate this way to x, we've got 3. So, which means here, which were the 3 here and the 3 there, which we can now transform this integral this way and say integral of 3x to the power 3 plus 3x to the power 2. And somewhere here write a nice 1, which is a 3 over 3, then brackets x squared plus 1 brackets dx. Where is this taking us to? From our analysis of the derivative of this, we saw that we are short of a 3 to get this to be a derivative. But then we cannot just multiply by 3 and get the derivative. We multiply by 1 because we know that any number a multiplied by 1 is equals to a. So by multiplying by this 1, which is 3 over 3, we haven't actually changed the value or the expression here. You see that identical. Then simplifying here, what you can do, we can multiply this 3 here and you get 3x squared plus 3 in brackets. Then we've got this 1/3 here being redundant. You can take it outside the integral sign as a constant and rewrite this way. X squared plus 3x in brackets to the power 2. Sorry, this is supposed to be 3, not a 2. Then now, if we now focus only, after this transformation, we focus only on what is the under integral sign, because the constant here does not affect this function here. We can integrate now like we did before, and then just multiply this result by the constant. So this is going to be equals to 1 over 3 x cubed. So this is x cubed plus 3x to the power 2 plus 1 divided by 2 plus 1 plus a c. Then simplifying this, we get this is a 3, this is a 3, we get a 9 here. Then we've got x to the power 3 plus 3x to the power 3 plus c. So that should be our integral. But obviously, since we were starting off, some of us will be doubting whether is this really this function which we differentiate to get what is under the integral sign there. Let's check. So what we do is we take our y here, y of x, to exact this function, which is x cubed plus 3x over 9 to the power 3. So what we're going to do here, we differentiate plus c, now differentiating, now of course, or differentiating this, we get y, little y, which will be 3x to the power 3 plus 3x to the power 3 minus 1, which will be 2, multiplied by the derivative of this argument, which will be 3x squared plus 3, all divided by 9 plus 0, being the derivative of the constant. Now simplifying here, we can see that we've got a common factor 3 here, which we can take out to here. We get 9 brackets x to the power 3 plus 3 to the power 2 over 9 multiplied by x squared plus 1. And then we can see from here that this 9 and that 9 will give us a 1. and then we are left with x cubed plus 3x, this is 3x here, power 2 multiplied by x squared plus 1, which is exactly our function, which is under the integral sign there. Otherwise, for now, thank you for listening.